In this video, I'm going to talk about the physics of objects in circular orbits around something, whether that's a satellite around a planet, or a planet around its star, or any object falling in a circular path around a massive body. And we're going to talk about how you could figure out how fast something needs to be traveling in order to be in a circular orbit, and if it is, how much time does it take to go around once? We call that the orbital period. For this video, we're going to calculate how fast the International Space Station needs to be traveling, what its orbital velocity needs to be, so that it can be in a circular orbit, which is about 230 miles above the Earth's surface, which is 370,000 meters or 370 kilometers. And you might think, well, why does the International Space Station have to be involved in a circular orbit? If it's, more than 200 miles above the Earth's surface, isn't gravity so insignificant it can just sit there and float? The answer is actually no. The size of the gravitational force on the International Space Station depends on how massive it is, how massive the Earth is, and how far away it is from the center of the Earth. At the orbiting altitude of about 370,000 meters above the Earth's surface, it's about 6,740,000 meters away from the center of the Earth. If it's at the Earth's surface, it's still really far away. It's 6,370,000. So when you go an additional 230 miles away, you're not really increasing the distance the space station is from the Earth that much. And it still feels about 90% of the weight it would. Gravity still pulls on it with about 90% of the force that it would if the space station was sitting on the Earth's surface. So if the space station was at rest, it's going to fall straight back down and crash into the Earth's surface. So the space station has to be moving around the Earth, otherwise it would fall to the Earth's surface. So what is the gravitational force doing? Well, if the International Space Station is in a circular orbit, that means the force of gravity points, well, we know it points towards the center of the circular path because it's pointing towards the center of the Earth. And that gravitational attraction is perpendicular to the direction the space station is moving at any point. So the gravitational force doesn't speed up the space station, it doesn't slow it down, it just changes the direction of the space station rather than its speed. And so gravity is just continually redirecting the direction of the International Space Station. It's not changing its speed, and it maintains a circular orbit at a constant radius at a constant speed. Well, it's not just any constant speed that will work. There's only a particular velocity that would work. So just to give you an idea of that, like I said, if the International Space Station starts at rest, if it's not moving, then gravity is going to pull it straight back down to the Earth. Well, let's give it a little velocity. Let's say a little velocity up. Well, gravity still might be big enough to make it curve and still fall into the Earth's surface. Maybe not right below where it started, but a little bit farther along the Earth's surface. What if we go a little bit faster? If we go just fast enough, it might be enough velocity so that it barely misses the Earth as it falls towards it, and then goes back to its original position in a highly elliptical orbit. And the faster we go, it'll get closer to the Earth, but it'll miss it by even more. But this is not a circular orbit. This is still a slightly elliptical orbit. And there's only one velocity that you could be moving at a particular height, so that there will be a circular path that it follows where the orbital radius is constant and the speed is constant. And if you go even faster than that velocity, it won't be a circular orbit. It'll again turn into an elliptical orbit. So let's think through some specific values about the Earth and the International Space Station to calculate how fast it has to be traveling to maintain a circular orbit. Well, what's the equation that you need to think about for anything involved in any kind of circular motion, whether it's roller coasters or cars going around curves or International Space Stations going around the Earth? It's this. We know that when we add up all the forces on any object in a circular motion, we know the sum of all the forces points towards the center or centripetally, and we can figure out how big that needs to be by multiplying the mass of the thing moving in a circle times its speed squared divided by its radius. Well, if you're in AP Physics 1, this equation is not on the AP Physics 1 equation sheet, but you can get what you need by combining Newton's second law and the centripetal acceleration equation to essentially give you this. So once we have this, and once you realize this is the equation you need to use, the only question is, what is equal to the sum of the forces on the International Space Station in this particular problem? Well, the only significant force on the International Space Station is the gravitational force. And so we have to plug in the size of the gravitational force on the left side of this equation. how do we know how big of a gravitational attraction there is between any two masses, in this case, the mass of the Earth and the mass of the space station? We're going to have to use another equation that we've talked about before, which is Newton's universal law of gravitation. The size of the gravitational attractive force between any two masses is equal to this universal gravitation constant times the mass of object 1 times the mass of object 2 divided by their separation distance squared. And that r is the distance from the center of mass 1 to the center of mass 2. So in this equation, on the left side, instead of the sum of the forces, let's plug in the equation for the size of the gravitational attraction, because the sum of the forces is the gravitational force. So we've got our big G constant, our universal gravitation constant. And what are the two masses? We've got the mass of the Earth. We'll just say capital M for the mass of the Earth. And little m will be the mass of the space station. And we're dividing by how far apart the center of the masses are from each other. And that's from the middle here all the way to the center of the Earth. And we're going to set that equal to mv squared over r. In this equation, remember, m is the mass of the thing moving in a circular path. That's the International Space Station, so we're just going to keep that as lowercase m. V squared, like that represents the tangential velocity of the space station. And r represents the orbital radius, the radius of curvature it's following. When we look at this equation, we should decide, are these values the same? The distance between the center of masses and the orbital radius of the space station? And the answer is yes, because either way, those both represent the distance from the middle of the space station all the way to the middle of the Earth. So once we have this equation, before we solve for velocity, and we're going to do this symbolically first and then plug our values in, let's simplify. Notice the mass of the space station, little m, is in the numerator on both sides. So let's divide both sides by m. So that cancels out. The mass of the International Space Station actually doesn't matter in this problem for how fast it has to be traveling. And since we said both of these r's are the same, then we can simplify further by multiplying each side of the equation by r. And if we multiply the right side by r, it cancels out the r in the denominator here. And on the left side, it cancels out one of the two r's in the denominator. So we've got one r left. Here's the simplified form of that. On the left side, it's just the universal gravitation constant times the mass of the Earth, or the mass of any planet, divided by the orbital radius of the thing moving in a circular path, is equal to the square of the needed velocity to maintain a circular orbit. And if you have this equation, actually there's a lot of problems you could solve. We're trying to figure out how fast the space station needs to be traveling, so we just need to solve this for v. And it's almost there. We just have to take the square root of both sides, and we get that the needed orbital velocity for something to be in circular orbit around any massive body is equal to the square root of the universal gravitation constant times the mass of the thing you're orbiting divided by whatever orbital radius you need to be at. But we could also use this equation. Like, this equation tells us how the mass of the planet and the orbital radius and the orbital velocity are all related to one another. We could rearrange this and solve for m. So we could figure out the mass of a planet just by, let's say, taking a moon that's orbiting that planet. And if we know how fast it's moving, if we know how far away the moon is from the center of that planet, we could approximate the mass of that planet in kilograms. Or we could solve this for the orbital radius. Like, what's the orbital radius that you need around a planet with mass m moving at some speed v? And so once we get this equation, we can solve all sorts of different physics problems about circular orbits. Well, coming back to the problem we're solving, we're trying to figure out the needed orbital velocity of the space station. So let's use this version of that equation. So plugging the values that we need, big G, or the universal gravitation constant, is 6.67 times 10 to the negative 11th Newton meters squared over kilogram squared. The accepted mass of the Earth, that's the planet we're orbiting in this problem, is about 5.97 times 10 to the 24th kilograms. And then we have to divide by the orbital radius, the total orbital radius, the distance from the center of the Earth to the center of the International Space Station. And that's going to be the Earth's radius, 6.38 times 10 to the 6th, plus the added 370,000 meters. So all of this right here is little r, the total orbital radius. So we find out that the International Space Station needs to be moving at about 7,681 meters per second. That's really fast to maintain a circular orbit around the Earth when it's, about 370,000 meters above the Earth's surface. And if you convert that into miles per hour, that's about 17,181 miles an hour, which is incredibly fast. But if it wasn't, it would get close to the Earth or potentially crash into the Earth or just not maintain the same constant orbital radius. And if you want to check what is the International Space Station doing right now in terms of how fast it's going and how high it is above the Earth, you can actually check a website called, just go to isstracker.com, and in real time it'll give you the approximate speed of the International Space Station and how high it is above the Earth. So if we just check it now while I'm making this video, it pulls up a little map and it shows you that the International Space Station, it looks like it's off the west coast of Africa, and it's following this yellow path here. And if we look over on the right, this is its approximate speed in miles per hour. We thought it was a little over 17,000 miles an hour, and in fact, at this moment, it's moving at 17,141 miles per hour, and it looks like it's about 260 miles above the Earth's surface. So our theoretical prediction is really close to what it's actually doing at this moment. Now that we know that the orbital velocity of the International Space Station is over 17,000 miles an hour or 7,681 meters each and every second, it's pretty simple to figure out how much time it would take the International Space Station to go all the way around the Earth once. Essentially, we call that the orbital period, the time for one complete orbit. Well, if the velocity is constant in circular orbits, then we can just use our constant velocity equation, or our average velocity equation. The average velocity is equal to displacement over time. And if we're trying to solve for the time of one orbit, we need to know the displacement, how far it travels in a circular path just once. That's the circumference of the circular path, which is 2 pi r. So we get that the orbital velocity, or velocity, is equal to 2 pi r over the time for one covering one circumference, which is the period. And so let's plug our values in. Our orbital radius, remember, is the Earth's radius plus the additional height, this 370,000 meters. So our equation becomes 7,681 meters per second is equal to 2 pi times the orbital radius, which is the Earth's radius, 6.38 times 10 to the 6 meters, plus the added height of 370,000 meters, divided by our unknown period. And if we multiply each side by period, we're going to move it over here, and then divide each side by our velocity. It's going to move the velocity down to the denominator on the right side. And the total circumference of one orbit, when you multiply all this out, you get 4.24 times 10 to the 7th meters. That's how far it travels. And it's moving at 7,681 meters per second. So if you divide the circumference by the velocity, you'll get the orbital period in seconds. Notice the meter units cancel. We'll be left over with 1 over the inverse of seconds, which is just seconds. So the period is about 5,520 seconds, which is about 92 minutes. So the International Space Station will travel all the way around the Earth once every 92 minutes. And in a 24-hour period, like one day for us, it goes around the Earth about 16 times, which is crazy because that means astronauts on the International Space Station, every time they go around the Earth once, they see a sunrise and a sunset. So in a 24-hour period, they're seeing over 15 sunrises and sunsets. I hope this video has been useful in helping you think through the physics of circular orbits, calculating the needed orbital velocity to be in a circular orbit, or to figure out how much time it would take to orbit once, or even thinking through the symbolic equations to solve for the orbital radius needed, or even the mass of a planet.